So hi everybody, thank you Paul for being with us today, and the floor is yours. So I hand over to you, Paul.
Thank you, Patrick. I'm Paul Hoffman, and my background is in physics, and my PhD was actually in renormalization group. And renormalization group is mathematically what is behind deep learning. So I happen to be the first person, actually, one of the first person who used deep learning to predict chemical reaction in a mass spectrometer. In 1986, when I was a postdoctoral fellow at Technical University in Munich. And I have been in machine learning AI, obviously, for many, many years. I worked for SAP, for BASF, Accenture, and I was the CTO of two startups, Saffron Technology, which was a competitor of Watson. We beat Watson almost always, except in healthcare, and we did a lot for Boeing. So if we have time, maybe I can tell you about that too. And that was an associative memory, which is the original version of deep learning. And we can talk all about that later. And then the other startup was Space-Time Insight, which was AI and IoT. And today I'm going to talk to you about failure prediction using probabilistic programming. And we'll talk about some of the advantages. And I don't know how technical you are. We can go in very deep detail. Yeah, that's what it is. So let me start. Here's the agenda. I first give you a short motivation why this is relevant and will be for the next 5 to 10 years. And then I shortly sketch the problem that I can talk about, which is prediction and maintenance and repair of pumps for a huge project in Africa. And then I will be talking about what type of model we had, what type of model we used, and basically first the prediction of the degradation, and then the optimization, the reinforcement learning, if you want, for then deciding in what stage the pumps are, and then how to repair them. So let me start here with the motivation. I have been using this slide for the last 8 years, and 8 years ago, I think it was pretty new, but it's somehow visionary in a deep sense. And I'm still learning every day about it. All companies in the world have those three problems. One is aging assets. It costs a lot of money to replace an asset and to put in a new one. And a lot of the world is the brown field where you cannot just put in new hardware. So a lot of times you have what's called retrofitting. You take the old hardware and you put sensors to it in order to analyze it and then do some machine learning. The second is, and this is becoming more and more relevant, it's a demographic problem. We have, of course, a shortage of the workforce, and in 2028, according to Deloitte, there will be 2.4 million jobs in the US missing, and this is basically manufacturing out of 60 million. And now, there is onshoring, there is a reindustrialization of the US and the Western countries in general, but especially the US, and this number will probably be much higher. And then the other number is a number that is as old as MBA is, there's a margin pressure. We try to be more and more efficient, and there's always a guy out there who is more efficient, and especially in manufacturing is a very hard task. And the EBITDA declined 11% from 2015 to 8.6 in 2018. And it's further declining. And then was it BASF? This is the biggest chemical company in the world. And BASF was very happy when it had 10%. And it didn't have 10% for a long time. So this is where we are. So what's the solution? How can you get out of it? And basically, the solution is it is software, it is AI. You have to increase the value creation using the knowledge that is in data and AI and machine learning. And in the end, the old traditional applications, if you think about it, the business applications like an SAP system is data into the database and then it stays there and you use a little bit in a business warehouse and you analyze, but when you analyze it, it happened already. And as an SAP system is a batch system, typically the next day. The new applications are of the kind that we will take the data from the process, from the shop floor, from IoT, and we connect it with business data and we react right away. And that is will be a new era, and basically it goes by the word software eats the world, or ephemerization, dematerialization. That's very interesting. You know, there's a beautiful books about the inevitable. It's a beautiful book I can recommend to you about how technology will control the future, and we are just at the beginning of an enormous jump in productivity. And basically what we want in the end is we want to have a new business model, and this new business model is pay per use. And this new business model is a full service. So we don't buy the car, but like Uber, it's Uberization. We just want to get from A to B. We don't buy a jet engine, but we want to have jet power per the hour. And this is the famous model of Boeing, and you all know of that. And there is where you want to go, but typically you start in the service. You want to start with a better service. You want to have less spare parts. You want to have a proactive service. You want to automate your service. That's where you typically start. You do remote installation. Then when you do this and you offer your equipment and you go away from the maintenance and you do the maintenance with spare parts and per hours, but you offer some functionality that you deliver, then you very fast bring out your design errors, your over-engineering goes away, you get a better experience for the customers, and for the first time the designer sees what the customer is using to think for. And then another thing is then condition-based maintenance. A lot of companies have it, but then you want to have predictive maintenance. If you want to be a Rolls-Royce or any of those companies, then you want to have predictive maintenance. You want to know when you have to service your engine, when it lands in the airport and when it has to be repaired. And this is predictive maintenance, and that's what I will be showing you, how to do this, to predict the part before it breaks, and then to know how to repair, to optimize your resources and which one to do first and then the next. So that's what we will be talking. This is, I just showed you this to give you a short motivation. So here is our problem. It is charity water. So this is it's also a problem, a proxy for what I can talk to. But it's a project in Ethiopia, in Tigray. It's about 30,000 pumps. They're connected in the cloud. It's a very cool thing. And here again, it's retrofitted. You have those pumps, as you can see here. And then you see here down the sensor, the retrofitted sensor, and it tells you about the situation of the pump. It doesn't measure really that the pump is broken or not, that you can't. It would be many more sensors, and typically, and that's very important to understand, we measure a hidden variable, and you will see what does it actually mean that the pump is broken, right? And this is unsupervised learning, so it's not that you categorize and train a system of broken or not. And anyway, in a lot of systems, this would be very hard to do, and we'll talk about that too. So the pumps have a 10-year lifespan. They have a very high failure rate. This is very distributed in the location-wise, and the technicians at the moment dispatched manually. But that's, of course, not good enough. You want to become more efficient. Now, why is this a hard problem? This prescriptive maintenance, the maintenance where you predict when the part breaks and then you say what to do. Well, there is an uncertainty in your asset state. First of all, like we said, often the asset health state is not known. You cannot even directly measure it. And even if you have sensors, they don't work all the time. Then, as you can very physically understand here with those pumps, your assets are very complex networks. It's a plant and a lot of facilities in a plant, and they come together and you go from one product to another. Or in this case here, you have just a lot of pumps that are connected, and if you don't have the connection right, the water doesn't flow. Then you have typically missing data, you have technical problems, then you have people, right? Then you have their skill set, you have the availability, last minute changes, and you have lots and lots of uncertainty that come from the environmental weather and so on. And that's a very, very hard problem to do, much harder than to predict something in the stock market. So what is our approach? And I think in this in itself, it's quite innovative. Besides using probabilistic programming for the prediction, which is, I think, a rather new approach. And if we have time, I tell you, we kind of invented it. But later we found that it has been there before, but not used for predictive maintenance. But this approach, we were unfortunately not the first, but it was more or less the same time. Also, we didn't publish it. We published it very late. So anyway, you have a degradation model. You determine the asset health, and this state evolves over time. It evolves over the future. And then when you know that the part breaks, that's not good enough. It's like in the stock market, the price goes up and down. You didn't make any money yet. Now here comes the money management. When to invest, how much, and when to sell, how much. And this is here, this is what you have here too. You have to have a maintenance policy. You have to determine the best action to take for the asset, right? At any given moment in time. And that's typically a reinforcement problem, learning problem, optimization problem. And then you have a resource allocation. You have to allocate the people, and then the location, the sequence, where do you do what, and when do you go from one to another location. So this problem consists of those three sub-problems, and we'll talk about each of them separately. And we'll start with the degradation problem. So you have historical data, and in most of your data, the part is not broken. All right, so you don't see broken. And what you want to do is you want to predict, and definitely you want to predict a failure, and all parts will break. But you have very few samples of broken parts. Actually, we have done prediction, and that's kind of counterintuitive, but it's also for the Q&A if you want to understand that. You can predict if you have never seen the part being broken. I once had a very hard discussion with a professor from University of San Diego. I couldn't believe that it is that. But that's what it is. And this is probabilistic programming. So you do not massage the data to fit the model. No, you do it the other way. So you have a model. It's a generative model, right? There are discriminative models, which are the regression models, which is the trees, which is often even LSTM or deep learning is used as a regression model. The classical regressions, boosted, anything boosted, lasso, whatever you can think of, what we have been using for a lot of time. But it's a generative model where you can generate the data, and then you generate the data, and then you see if it fits with your observation. And the cool part is, of course, you can generate the data into the future. You can also generate data from very few data and see if it fits to the model, and then do simulations and all kinds of stuff. So that's what that is. And now, practically, what do you have? You have this asset type, you have a time, you have a status, as you see here, it's okay, and then it's broken. And then here on the side, you have the value. And why it's kind of trivial, and I did it a little bit unorthodox, right? But why do I point this out? Well, because the point is you observe your data in the seconds, in the microseconds, in the milliseconds, we have all done that, or in the minutes or the hours, whatever it is. But you do not observe the breakage necessarily because it happens during one of those windows, and then it is there. So you cannot do a simple classification, a simple discriminative model, a simple regression, a simple classification. It would not work because often the broken part is not in a window that you have observed, right? So basically, you know what I mean? That is the part here where the last step for it breaks, right? That is not very well defined. Now here a very short recap on what is finite hierarchical mixture models. You have a genie, she has urns, she has a distribution, she takes them out. All you observe is the conveyor belt, and you observe Y, which is red-green. And what you want to guess is the distribution that she has here of those balls in the urn. And we did this the first time we did predict, we did profile the taxi cab. When we did this the first time, we profiled the taxi cab drivers in New York. And imagine you come from the mass and you want to take a cab driver and you want to know if he's going to cheat you or not. How do you do that? That's very tricky. It would be super naive to take an average value of the fare, and if he's off or of the fee, it's not true. It has to do with the location at the time that you drive. And I presented this once to the CEO of a company that was trading commodities, and he was an MBA. But he understood that, whereas many data scientists do not understand this intuitively, that, and even technical people, that you have many averages that you want to predict here. So this is not an ARIMA or some moving averages or anything like that, absolutely off. You wouldn't understand that. They are very intertwined. So basically that's what it is. You observe here, you have your distributions here, and you observe and you mix them in a certain way, and the mixtures you observe, and then you have a speed, and this gives you archetypes of the highway, the city. If the car is parked, of course, no, then you have very little speed when you go in, and then you can profile the drivers. Are you a commuter? Are you a professional driver or not? Well, and another approach to come, and I think I have to cut this a bit short here, but if you come from topic modeling from LDA, if you're in the Silicon Valley, you know, Michael Jordan made this very famous in the 2000s, and then every meetup was about topic modeling. And then what do you have? You have a finite number of words. You have very few topics. That is your regularization. That's what you predict, right? And then you have an infinite number of documents. And so now think about it. You can understand that even if you've never done time series prediction, that's not necessarily, time series nothing to do with time, of course. It does not have to have necessarily to do with time. Let's say that way. You have the trips, and it's the types of trips, and it's a finite number, also some couple of thousand. And then you have the spatial distribution. These are the topics. Are you driving from Manhattan uptown, Manhattan downtown, or Manhattan to Queens, or whatever? And I'll show you that a little bit. And then you have the drivers, and there you can have an infinite number. And the trip is the pick-off location and drop-off location, right? This is the pair, the time, the fare, and so on. And the drivers are like a count, and the profiles are mixtures. And you can use exactly the same approach, and we did that for fraud and for predicting, of course, which is even more important, what the NSA does, cheating, terrorism, and all kinds of things. So that's basically what we did. You learn from millions of trips, the pickup and drop-off, and thousands of drivers. And what you find out is you extract these archetypes. You extract those types of trips, those profiles, and you see these are the drivers. On the left, you see the entropy, the measure of uncertainty. And after already 100 trips, you have a profile for each of the driver. And then you can see if they are cheaters or not, or if what they offer you is in their profile or not, and so on. I don't want to go into the details too much, but you have those topics, and each driver is a mixture. And I'll show you this then on this very concrete example soon, but I wanted to give those people who have done text and have done never time modeling, I want to give them a hint how this works. And here you see this, you have this drop-off and pickup locations, and then you have the tourists, you know, they come from Central Station and go to the Statue of Liberty and whatsoever. And then you have the commuters, the bankers, and you have the rich ladies in Upper Town Manhattan. They go for lunch, or they go to the pet store and whatever. And you find that you don't know anything. This is totally unsupervised. And I give it those nice names, and they are just funny. But you find this all unsupervised. Well, and now imagine we still have the same conveyor belt, but now we want to guess, did the genie take the ball from the same urn, or did she jump? And that is when we come to a hidden Markov model of topic mixtures, or of tight topics. That's how it was called originally. And that's what it is. You have those states, you have the transition, and you give out red or green balls here, right? And this is what you see here. And then you can make this, of course, more general. You make a distribution. Here in this case, it's a Gaussian, but actually it can be any And in reality, it's a distribution of distributions. If you just do this with Gaussians, you don't get anything. Nothing in the world is really Gaussian. Very few things are Gaussian. So this is a little bit what it is. You have your states, you have a present, the past, and the future. It's the Markov model. You don't see the states, you observe data, and the states are modeled by mixtures. And this has the advantage, you don't need to model each state. You don't have need a distribution for each state, which is very important because you can have a lot of states, hundreds of states. And then secondly, we have, of course, the curse of dimensionality. It's a very sparse problem. And having a few distributions, let's say 10, and then build 100 states means you have a regularization. And all you have to find are those 10 distributions. That's why you work with distributions of distributions with the mixtures. And this is the only formal slide I put up here. This is a little bit more mathematically what you do. And basically you can read it in the paper, but you have initial state distribution, a transition state matrix, which defines how you go from one state to another. And then you have those states that you observe. So basically you observe the state, you come in with guess a transition state matrix, and then you can propagate your initial distributions for those assets till they break. And that's what you can see here. So here you have those states to begin. In a healthy state, you always begin, it's a diagonal matrix, a transition matrix. And on the left is all zeros. You always go to the right. You have the one probability of 1 to be in A. And then it moves, and it moves over the different states. And as you can see, all states end in F. This is the final state. But there are different ways to go. And each asset is individual. So each of the 30,000 pumps is an individual distribution. Still, you can make say something about all those states, which we will do, as you see in the next slide. We can have an average degradation. We can have degradation curves. We can have survival times and all that. And that's basically what the system delivers. It's a generative approach. It's very, very beautiful. It's quite nicely to solve for very large problems. This is, of course, a toy problem I show you. Basically, that's what happens. You see, it happens in the D, and it could go now to the F, to the final state, but it goes over E, and then it goes to the final state. So we'll use this type of, and there it stays. So there's a probability of 1 to be in F, and a probability of 1 to be in A. So that's basically what that is. Here again, you propagate the states. You always end up in F. The states we don't know, we have to guess them, and they propagate over time. And what is a asset is still good, it is not so good. How do we come to this meaning? I will show you, but it's not in there. And some people ask, are these states real or not? Some states you recognize right away as real. Most of them are real, and I have seen those states that have no meaning. Sometimes you have chunk states for the things you did not understand. Those states have then no meaning. The cool part is you can include historical information, since this is Bayes reasoning, right? It's a Markov model, so this is a subset of Bayes. You use the Bayes formula. That's also the way how you solve it, as you saw in this other slide. There's a Dirichlet distribution involved. What is the cool part about the Dirichlet distribution? The Dirichlet distribution is the conjugate prior or posterior of the categorical distribution. So if you have a categorical distribution, you always come to a Dirichlet, and then you can go on. That's why you have a chance to do this, to solve it computationally. That's kind of like an eigenproblem in physics, right? You have an eigenvector and you get back the eigenvector. You can incorporate your historical information. You can also correct. You can because you calculate the posterior, you didn't see, you made a mistake. The model gave you the wrong result. You can say, no, that's not right. And then you have another posterior corrected one. The model says the part is broken, but it's not broken. You observe it's broken, and the other way around. Missing data is no problem. Also, the interval in the data is no problem. It can vary. Very important. So this methodology is very robust to missing data. Now here you see this is the transition matrix. Like I said, you go from left to right. Here you have Poisson distributions. This is an example of disks that broke. That was the second example. We went to a data set and it said, we will predict you the disk better than the Hitachis or the Western Digits or whatever they had. Were still rotating disks in those days. And we do this, and this is a Poisson distribution. And you can see state number 1 has mainly the topic 4, and I have to move this thing at the topic 6. And then state number 2 has mainly the topic 5. All right. So that is the very cool part. And if you observe this very carefully, if you go from one topic to another one, you have a non-Markovian process. But for the mixture of the topic, it's a Markovian process. And now what is so cool about it? You can, as an engineer, you can incorporate your knowledge. You can decide, no, there is no transition from this and that state, because we know it does not happen. That also helps you in the calculation, because it accelerates your calculation. You have to calculate less, right? You have less computation time. Another thing that is very important is right censoring. When you have the degradation, or when you have people dying or stuff like this, you have right censoring. Like we said before, think about, you would do this with classification. You're one state before the part breaks, and you don't know, is it degraded or not, right? And it can be because you just have not seen the degradation, because it's in the window that you don't have. And then you would have to throw it out in a classification problem, right? In a supervised problem, you can't use that. Here, no problem. And this gives you statistical strengths, and you get much more data. And like I said, in most problems, you have very few broken states, sometimes none, and still you can do a prediction. So that is very important. Think about how would you do right censoring if you use LSTM for time prediction. People have tried to do this as a non-trivial thing. And in general, whatever methodology you use, how do you use right censoring? There are some who can handle that, but they have other disadvantages. So this is how this looks. We have the sensor, we have the states, right? And this is how one individual asset propagates over time, over the states, all right? And now we do the prediction. We have a couple of, oops, too fast. We have a couple, you have to be careful not to touch it too much. We have here our sensor, and in this case from the pump. And then we have, we calculate the posteriors, we calculate another posterior, we go over time. And this is the forecast, what you see on the bottom. These are the states that we forecast, and this is the failure time. And as we move on, the failure time becomes closer and closer to the true. So this is also very beautiful. There are some systems where this jumps, where there's absolutely no relation, sometimes huge jumps, here not. And you can see already after 250 observations, we have a pretty good estimate for the failure. So the model, the accuracy of the model improves with more observations, as it should be. And you can start with very few observations and it's valid, that you don't have to change anything, nothing in the model, nothing in the data massaging, and so on and so on. So now, like I said, what happens is you have profiles. You have certain ways things degrade. I don't know where you come from, but another thing, we did this battery, I can't talk too much about it, except that we did it for Panasonic, and I can say we found a construction error, right? First, we thought our model is wrong, but we found a design flaw. But basically what you have there is there are two ways that the battery degrades, the normal way and the catastrophic way. And we could predict that without having ever seen the batteries degrade, because they haven't seen it, they just manufactured them. They only did some things in the lab, and that's another presentation, and it's like, and you have to be very careful about confidential information there. But basically you have those profiles, remember those taxi cab drivers, they have those profiles, they are those mixtures. What is that for you people who come from topics, on topic modeling? Yeah, these are the documents, right? These are the documents, and they have certain types of topics, and they share. So that is the very cool part. You learn from one distribution, or you learn one distribution in one profile, and then you can take it over to another one. And so you have in these pumps too, we found here basically three types of profiles, three ways of how they degrade. And you can have 5, 6, 7, and you don't have to increase your number of distributions to calculate, to optimize, to find through an optimization, because you use mixtures, right? You make the topics, so you make mixtures out of it, and then the profiles are just mixtures of those topics, and that's what you see here again. And then you have a survival curve, right? Classical survival curve. If you have been here, there are classical methodologies how to do survival curves, but none of them has this property that you have all the correlations between all the input variables and the output ones. And this is the advantage of a generative approach. Well, and now let me open up your mind and show you one thing. The prediction that you do depends on when you predict. That's very interesting. There is no one prediction. Prediction is high dimensional. But if I predict today, the path will break pretty soon. If I predict a little bit later, it will break less. And then the prediction, the probability goes up. And this is just one profile. And here people say, hey, how can that be? Why does it change over time? And this is kind of a lot of hand-waving explanation. And then they say, yeah, no, your paths heal. And if you talk to engineers, they understand that. But the coolest thing I had is when I talked to my friends, you know, I know a lot of people in the Silicon Valley. We got into this AI topic in the 2006s, 10s. Till then, nobody was paying attention, even in the innovative Silicon Valley. This was very local. So this is a friend of mine at Tesla, and his task was to predict when they have to recharge the battery. And he says, yeah, this is exactly what I get too. If you drive up the hill, you have a lot of drag. This is your prediction. So then you have to go to the charging station. If you're then on top of the hill and you have another part of your route and you don't know which one that is, right? And you have these new parameters, it goes here. And then at one point, no matter what you do, you have to recharge the battery. So this is very cool. When you see a battery charge on your computer, it has absolutely no meaning. You know that when you say 20% and then it's all gone, especially with this Dell here and this Windows stuff, it's totally off. It never tells me when to really get back and recharge. You just can't do that because you don't have this dimensionality. So good. Now, here we go, and here I show you again the entropy, and after 50 observations, so people ask, typically I've made this from the questions that people ask. After 50 observations, you see the entropy is already pretty small. I have little uncertainty. We understand the profile. So we know, okay, this belongs to this profile or that profile. So we don't have to even observe that much. Think about the taxi cab driver. We know, does he cheat? Does he cheat a lot? Is it pretty, does he, and what does he drive? What types of drives does he do for the tourists, for the Wall Street guys, or for the commuters? And the same thing is here. And this is this idea of archetypes. This is beautiful. This is the regularization. Machine learning AI is, of course, regularization. It's a compression in some sense. And these archetypes that's what it is, and that you can use in marketing. That is that's how you profile the cheaters. It's how you profile terrorists or bad people or whatever. Yeah, and now then there comes the question of accuracy. Yeah. So, well, this is a change point detection problem, right? Change point detection problem. So this is not a ROC curve, right? This is not a regression. This is not a classification, nothing of that. It's not a discriminative model. It's a generative model. Accuracy, what does it really mean? So let me explain this here. And the solution is, of course, you have to go to the practitioner and you have to give the practitioner a solution. And the practitioner says, I can afford 10% of my parts breaking. On the left, you have all parts and they are good. And on the right, all parts are broken. So you can have two strategies, broadly speaking. You can say we repair the parts before, so that we are sure that we have only 10% parts broken, and you do preventive maintenance. That's what we did at BASF in the 90s, and that's what the Air Force does. The US Air Force, for example, when they repair something, they always change the battery in the flight recorder. Now, yeah, you right away see you leave a lot of money on the table. And then, sure enough, in the 90s, the airlines, they started to save money, and some smart guy had the idea, wait, we don't replace the battery each time we have the plane in the repair shop. on the ground, and we have to get the technician in. We only replace it when it breaks. Guess what was number one problem for the delays in the mid-90s for airlines? It was the battery in the flight recorder didn't work. So this is also not the model, because then you're on the right side. So this is random here. This is the red curve, and here you see curves of and think of and it's actually taken from that. Think of the data center and your disks, and then you have Western Digital gives you a curve. They give you a condition-based maintenance curve, and so on and so on. And then you repair your parts, and this is the curve we give you. And then you see here, oh, this thing moved actually up. It should be down here. Here you see you can afford 12% breaking part. So here you go on this curve, you have 250 hours. This is your average uptime, right? Or you have this, and our curve has almost, it has almost 600. So I give you more than 300 more hours. That's what interests you. You want to have a very steep curve. You want to know when it goes up. And don't forget, this is the average. That's already important, but I can do it on an efficient basis. So accuracy is not the question. It's not the question. The trade-off is, how long can I wait and how many repairs can I afford, right? And that's what the part is. So accuracy is actually orthogonalities. Sometimes the accuracy of this curve is less than of those. Doesn't matter. If it is less, what you have to do? You just have to put more spare parts in inventory. You have a counter strategy. So accuracy is not the most important method. That I want to give you home. If you didn't understand anything in this talk, think about it. This is risk. If you talk to traders, no problem. They understand that right away. But as a practitioner, you have this risk problem. So now we know when the part breaks. Now how do we proceed? So what we do now is we take a very natural extension. So see, we have these states that we don't know. They're not observed, but we have them. We have a transition, and we go in with a partially observable Markov decision process. The Markov decision process has this very natural connection. The name kind of indicates it, but it's more mathematical. But there's a real deep connection that is to the Markov decision processes. And the Markov decision process has an action, and it has a reward, right? And this is an observable, this what basically happens. And the action is, we make it very simple. This is a toy problem for you to understand. In the reality, it's a bit more complicated. But we say do nothing, repair or replace. Those are our three actions that we can take. And we want to optimize that. And this is a subgroup of reinforcement learning. It belongs to reinforcement learning, a BOM-TP, a Markov decision process. So we find an optimal policy to decide what to do, right? And what we need is a value function for that. And we go where the value is the highest. That is what we do. And you think of a robot that wants to get out of the maze, and what the robot can go forward, sideways, backwards, and what does the step that the robot takes is where it's the highest value. Or you play chess. Actually, chess is nobody has solved that yet. But the Go is the famous example that Google did. So that's what you do. And I'll show you how you come to the surfaces. This is also simplified, but you have nothing, repair, and replace. And then here you have your distribution, right? And then here you have a high probability of failure, right? And then you go up and you want to repair. And the next state is you have less of a probability. I have to get my animation right here and move the zoom stuff. Yeah, okay, you saw this already. Sorry to go on back. Yeah, and then you see here, you have to do nothing, right? And you can see this. This is you have still greenish states and then red, and only if you see a lot of brown or even purple, then it becomes interesting. So this is how you do this. How do you come to the value functions? Of course, very high dimensional. Right, you have for each of those states, you have such a value function, replace, repair, to nothing, and then you want to go to the highest value, and this is in a high dimensional world, in a hyperspace where you go. And in this case, it's piecewise linear, so this is hyperplanes. And of course, you have to get the cost function, right? You have a value function, you have an objective function, and for that you get the cost function. And the repair and replace may be easy. The repair is the cost. You have to do this and replace. You have to build in a new pump. But the failure is not that easy, right? The failure can be all kinds of things. It means they have no crop, or if it's a nuclear power plant, the failure is very big. The failure is usually not so easy to estimate the failure cost, but that's what you do. Alrighty. So this is the first step. You see here, we go back to this thing. This is where we're talking about. So this was our maintenance policy. We determined what do we do for each individual asset. And now we come to the resource allocation problem, right? We determine what is the right task to do. So here's our resource allocation problem. We have the people. I hope you don't see this, so that's kind of okay. You have a crew, they have a skill set. You need sometimes a combination. In this case, not so much, but we did this also, of course, for the maintenance of windmills. And then you have, not every crew member can do anything. As you can imagine, of course, there's mechanical part, there's electrical part, there's software to be done. So you have to figure all those things out. Then you have the changing demand. So this is what we get from the model before. In this case, it was repair and replace. That's very simple. If you do nothing, it's not an input. That is our action. And then this is the stochasticity. This is also called stochastic optimization, right? Or decision making under uncertainty. And this, where there is the stochasticity, are the people sick or not? And you have constraints, lots and lots of constraints that you put in. And this is in here, the inventory, the tools availability. You can have thousands, 10,000s of constraints. You cannot have 10. Yeah, there are people who can solve this. Warren Powell, for instance, which from Princeton, which I would like to call out here, has written a beautiful book about that. I think he can handle 10,000 variables in stochastic optimization. But the biggest I have done was 2,000, 3,000. So that's a bit what it is. But like I said, it's a separate presentation. You have state variables, you have decision variables, you have exogenous information, you have the transition function, and you have your objective function. And again, you find an optimal policy. We don't have time to go into that. But what I show you is kind of what I can show you as the solution. Here you have the parts, you have the pumps, you see the history, you see you see this recovering, right? More degraded, and it comes back. Very interesting. It doesn't happen all the time. Often it is like our intuition, it becomes worse and worse and worse. But no, it can recover also, and that's maybe also for the Q&A. If you're very smart and you observe, there is a statistics that comes from breaking of the part, and there's a statistic that comes from the people, how they use it, all right? You have, and I saw this, we did some stuff for Union Pacific. You have the engine, and then you have the operator of the engine, or does it go up the hill or down the hill, east, west, and stuff like that. The locomotive, that is. And so you have to also profile. And this methodology, of course, allows you that. When we did the batteries, we did also profiling. So you have how the people use it, and then you have the statistics of the part, of the machinery, of the asset. And that's what we have here. And what you also can see is, since this is Bayes reasoning, you can see your confidence interval. And that is a problem for the people who do LSTM also in self-driving cars. The confidence interval is very hard to get, and you have to do then a variational Bayes, which I don't have to do. They have to do it because why? The posterior is hidden in the weights. So they have to do then a variational Bayes in order to say, is this good or not? And can we rely on the data? Is this really a pedestrian, or in the semantic segmentation? That is, you get in your pixel, you do the semantic segmentation. Is it a pedestrian, or is it only is this a light pole or whatever? So anyway, we don't have this problem. We can know how sure we are. And we show this, we make it transparent to the operator. And we give the outset condition, we talk about money, and then we give the instruction, we have the person to go, and so on and so on. And this is kind of very nice. And in the real world problem was a little bit more complicated, what I can show you here. Now I would like to finish, and then people ask about the tools. In Space-Time Insight, we programmed it ourselves, and we definitely were one of the first there in Scala with Spark. Later, in this example, we use Stan. I'm a big fan of Stan, comes from Stanford, as the name says. Pi MC3 is also interesting. Probably at the moment the big stars are GEM-MIT and Turing, and they are done in Julia, if you're familiar with that. Then the star student of Michael Jordan, David Bly, he does this project, Edward, right? What's the problem? The mathematical problem here is the partition function. How you know the partition function, calculate the partition function of your word where you have all these joint probability distributions is brutal. And you have to find approximations. And this is where very mathematically smart people, or can call me, I would say, computer scientists who know a lot about statistics and mathematics who go there. That's Edward. And then I love a tool that is Pomegranate. That was originally yet another hidden Markov model. It's very nice. It's a Python tool. It can only do, unfortunately, one GPU, but it is one of the best statistics packages out there in Python. And also it explains to you that hidden Markov model is a regularization of finite hierarchical mixtures of LDA2. They explain this, they have it very naturally. They observed this also a while ago. And we saw this, that we understood this the first time in 2015. More or less, I guess, when those guys did it too. They explain it very nicely, and you can go there to hidden Markov models with any types of mixtures of distributions. So that's it. That was the team. Jason Landerman, a very gifted mathematician that I got from the Livermore National Labs, and I'm not sure what Jason is doing now. They are very good friends. He was at Accenture, then he's now chief scientist of most of our team after the acquisition, or even a little bit before. Moved to a company that's called AppOrchid. Said was actually an electrical engineer, and he became a very gifted data scientist. And then Alan McCord, my brother in crime, he was my chief scientist. We are post physicists. That's what it is. This is the paper if you want to read a bit about it. I thank you very much for your attention. This is where I'm working now. If you want to get in contact with me, my email is very simple. It's paul@paul.email. So I guess we open it up for questions. I'm having a time check now. Oops, I took quite long, but all right. I hope you're still there.
We are.
So go ahead and ask questions now.
Okay, let's see if there are any questions, or the people are still thinking about your presentation. That's my case. But one question I have, you said you use this method for pumps in Ethiopia, right, as a kind of charity project, but was it used in other like industrial projects? Or
yeah, we used it a lot in industrial projects. So I have used it, I have to be careful. I have used it for a big aerospace and defense company on the West Coast.
Okay.
We have used it for Panasonic. That is, you can find this, I think it's on my SlideShare, so I'm not sure what happened to SlideShare, but I can send it to you. Yeah. We used it to predict battery degradation.
Okay.
We used it to predict gearboxes, which is important for choppers, of course, and for certain types of choppers. I can't say too much more about that because then you know which type it was. Yeah. It's, of course, also important for windmills. The gearbox is the part that breaks. It's also, we used it for turbines on planes and in for utilities. Yeah. Space and Insight was the market leader for utilities. We had 8 of the 20 top utilities in the US. We had the 2 top utilities in Europe, E.ON and RWE at those days. What did we use it else? I'm using it now for whole plants and for parts of plants, how to bring them together. Yeah, it is, in my eyes, it is the methodology. It works. So the finite hierarchical mixtures, why don't we use an LDA? Of course, if you're a mathematician, you want to use the continuous version. But the nice part about the finite hierarchical mixtures, in the continuous version, you have only one parameter, right? It's like you have 3 points and then there's only one way to put a line in between. But the finite hierarchical mixtures, you can bring in your engineering knowledge. And that is very advantageous. And it works for all distributions that belong to the family of the exponential ones. And that is almost all of them. It is Poisson, it is Gauss, it is linear. It's also a way to have regressions. A lot of problems are solved with regressions, but you have 2 regimes. Beautiful. You let the system find out where those two regimes start and begin, or 4 or 5, a degradation typically, like in the batteries, chemicals or whatever. You take the logarithm of it and you have something linear, but it's many linear ones. It does not work for, of course, for the logistic regression because it doesn't belong there. But I think we used it for lots and lots of problems. It works very good for fraud. Yeah.
And I guess you are partnering with different industries, right? In your research, right? You have partners, right? You have partners from private sectors. You have companies you're working with, right? At the university you're working with, right?
Yeah. At the university, we have partners, and also in Accenture, we had partners.
Okay.
Which is because, I mean, on the, yeah. So also, you have to have, this is an interesting question with data science. Can you do data science without domain knowledge now? And the difficult problems, you need a lot of domain knowledge. On the other hand, you are a good data scientist, or like Seth, for instance, he was an electrical engineer, he learned data science. You can come from the other side too. But you learn at one point the domain knowledge. And then you don't need a partner or anybody anymore. Then you understand the problem very well. But if you go into a new field, you haven't been there before, you don't know. So Jason, if you the history, he worked, like I said, he was in the national lab. He did the AI for the three-letter agencies when they listen to our phone. That's what he did. I can do that because I don't have a clearance. I can talk about it. He would never say a word about it. And that was, we were experts in fraud and cybersecurity. So how do you understand that somebody got in, and what do they do? By just looking at the TCP/IP traffic, looking at very funny things. And basically what you do is you build a graph, right? This is probabilistic. This is a probabilistic graph. So I always say everything in the world is a graph, and every problem is an optimization. And then the optimization is to find how the distributions are on the graph.
Okay. Oh, well, my question, I didn't formulate my question very well, right? My question was, okay, I guess you have projects with the private sector, with different companies, and then you're applying these models or these algorithms to concrete projects. That was my question.
Yes, because you even apply it to a very simple question. They want to know, what does this curve look? If I have the capacity for 10%, my people can repair 10% of this plant or 10% of the disk in the data center, to use an example that we all understand. Yeah. And then tell me what will be my operating hour? So this was also the question for the batteries, right? You are the CEO of a company, and they guarantee you that that was the mandate of the Japanese government. They guaranteed that these batteries will run for 10 years, and the capacity can go only to a half. If the battery does break in between or so, they have to pay. They have to give you the electricity for free or give you a new battery. Yeah. And because that was after Fukushima. So the batteries are like the size of what Tesla has. You charge them during the day with photovoltaics and you use them in the evening. But nobody has seen how this happened. So you know the CEO, and you want to know, do I have to put 5, 10, 20, or 100 million on the side? It's a very, very concrete business question. And now we go in and we try to find a guess. And I have another problem was converters, for photovoltaics. This is in California. If you have a photovoltaics, it comes from China. It's not that guaranteed the full lifetime. So you get the money from the bank. The bank says you need an insurance for 10%. And we went in and we said, okay, no problem. We can take 5% off, 2.5 you take and 2.5 we take. So typically we come to what I said before, to a business model that means it's a service, right? We deliver on a service. And a friend of mine, he does it, he took over the energy of a company.
There's another question here from Tuno Silva. Did you see any application of HAMM together with mathematical optimization once?
Yeah, that's what I showed you. What do you mean with mathematical optimization?
Yeah, I think you can. Okay, I can ask to unmute.
Well, you look here, I have this is what I showed you basically. I showed you, this is the trick. I showed you the tight mixtures, right? Mixed membership models propagated over time. And then you get when does the part break? And then you need an optimization in order to decide in what stage this thing is in, right? And also what to do. And you can put this all in one optimization. There are cases where you do that. When you have a more sophisticated model, you can put this all in one, but we just separated out here because we had to prove it, and this was very new. But you need a model. Think of it, money management, when to buy, how much, and when to sell. That's here too. Which part to repair, which person to send, you want to optimize, which part put on the inventory, how to put the crew together, and so on. So this is the gist. I think this is what is very important, and what we realized early. A prediction of a degradation on itself can be nice, and if the optimization is simple or you have enough resources, no problem. But typically you have a prediction and the optimization problem, or you have an optimization problem. There's a very sophisticated prediction and it's valid.
Yeah. All right. I hope it answered the question.
Or you can ask me directly if it didn't answer. Maybe they meant the optimization, how to come to the solution of the hidden Markov model. That's another optimization, of course.
Anyway, everybody can connect with Paul on LinkedIn, and usually Paul is replying quite fast, right? So that's good. Anyway, that was very interesting, Paul. Thank you so much. We're gonna publish the video on the community site anyway, right? So. And yeah, thank you so much for taking the time to present to us, right? And yeah, have a nice weekend.
Thank you, Patrick, for having me, and thank you to everyone.
Thanks everybody for attending.
Yeah, for some of you it might be late.
Thanks a lot. Thanks everybody.
Bye.
Bye.